Let's get started with the second morning session. So we have Rajesh Jayaram from Global Research, and he'll talk about multi-vector representation and embedding-based nearest neighbor research.
Thanks, David. So so I wanna talk about sort of a number of different problems and survey a number of problems and a number of results that come up when we try to study this new way to represent data. This is the so-called multi-vector representation of data, and it's something of a new paradigm in a way to work algorithmically with data. And so I'll begin by sort of motivating why we need a new paradigm, and then when we switch to this thing, what are the things that come up. So I want to start. Put it this way. Okay, so I want to start with sort of a very simple but very fundamental problem that's essential to a lot of machine learning, which is how do we compute similarity between data? In particular, non-mathematical data like text, images, video clips. How do we understand how similar they are? And historically, there's a lot of things that were done, in decades in past, like handcrafted heuristics. So you could look at bag of words, how many words are overlapping. You could look at pixels and pixel colors. But of course, we now know that the modern approach to these kinds of things is to use neural models, neural similarity models, to understand similarity between images, for example. In particular, I want to focus on one kind of neural similarity model. These are the so-called embedding models. And what do these do? Well, they learn some function which maps the data to a high-dimensional vector. And sort of the magical thing about these high-dimensional vectors is that in the embedding space, the L2 distance gives you an understanding of how similar the underlying points are. So closer the vectors are together, the more similar these points are. And so I'm sure many of you are quite familiar with these things, but I always like to stress it because it still blows my mind every time, because it's like it's this magical thing that allows us to transform something that's totally non-mathematical into something that's mathematical and allows us as algorithms folks, theoreticians, to work on them in an algorithmic setting. And so this is sort of, you can see why this may be interesting and useful. You can imagine using such a model to embed all the websites on the internet into high-dimensional vectors living on the unit sphere. And then someone comes along with a phrase like Abraham Lincoln. You can also embed that on the unit sphere, and you can find what vector was closest to it. For example, the Wikipedia page on Abraham Lincoln, or this White House page, they have the smallest Euclidean distance. And you can see why that would be useful, for example, for web search. And indeed, this is a special case of sort of the, what I think is like one of the key uses of embeddings, and that's information retrieval. So the idea here is I have some document data set, think of it as Wikipedia, and my goal is to pre-process this data set, ideally, fairly efficiently, such that given a query, which, it has some measured way of being compared to elements of the data set, I want to very quickly return the most similar documents in the data set to that query. And importantly, quickly here means faster than a linear scan. I don't want to look through every single document and compute a similarity. I want to do something sublinear inside of the data set. That's the good thing. And of course, we can use embeddings by taking all our documents, embedding them into the embedding space. Then when the query comes along, we do the same thing. And it turns out that there's a large number of data structures that support very efficient vector search queries, very efficient nearest neighbor search queries. They'll find you a nearest neighbor to that vector, and that's how you solve this information retrieval problem. And this really is like sort of the the basis for all modern information retrieval in industry and search all over the place. With some bells and whistles, this is sort of what's going on. One of the main things. And in theory, this is just a very well-known problem, which is approximate nearest neighbor search, which is the problem that I'm given some data points that live in some metric space X. And I'm also given, say, some approximation factor C. And what I want to do is pre-process this data set. Again, I want to pre-process it efficiently, maybe not in exponential time, such that given a query, which also lies in the same metric space, I want to quickly return a C approximate nearest neighbor. What is a C approximate nearest neighbor? Well, it's any point which was then a C factor of the distance to the true nearest neighbor of the data set. So I think of it as like these two annuluses. The nearest point is the distance in the smallest annulus, but I'm allowed to return anything that's in the larger annulus of the C factor expanded. Of course, you can imagine that if C is equal to 1, this is actually impossible to do for most metrics in some linear time. And sort of this isn't going to be that important for the talk, but the gold standard you can think of is like a nearly linear time algorithm in pre-processing. So for some small epsilon, perhaps it depends on the constant c, n to the 1 plus epsilon pre-processing time, and then sublinear query, n to the epsilon query time algorithms. This is sort of what I think of as the gold standard, and this is indeed possible for many measures. Okay, so I want to begin by now thinking about, this has been a very successful paradigm in practice, but there are some notable issues with it, and there's some notable just like with the limitations itself of representing data by a single vector. And I'm going to bear with me here. I'm going to go on a bit of a journey. We'll see sort of intuitively what are some of these issues with a single vector representation of data. Now, what these models sort of do is they're able to capture all the conceptual information or details of, let's say, an image into a single vector. But different parts of the image, especially for complex data, have, correspond to very different parts of the embedding space. And so you'll see that these models actually have a vector, which is like a direction in space, which corresponds to dogs. This image here has some dogs. It's a little blurry, but you can see there's some birds flying in the background, and then there's a woman wearing a dress. And so there's also a region of space you'll see in these learned models for like dresses and a woman and also birds. So we have complex data that contains these multiple concepts, and each of these individual concepts can be well represented by some region of space, which captures the nuances and details of that region of space. But the issue is that we have many concepts. How do we decide how to output a single vector which represents this entire painting here? You can see here that maybe there's, if the model just focused on the woman, it gets maybe some vector here. If it just focused on the birds in the background, maybe it would get another vector. So in practice, and this is not exactly what goes on, but generally in these neural embedding models, they have a pooling layer at the end. They have many different embeddings going through the transform model at the end. We pool all of them together. So we're just averaging all of them. So in some sense, these models, really what they're doing is they're taking the average of all the concepts that were learned in the image and outputting a single vector, which is the average. And so I want to claim that there's some downsides to this sort of averaging. So imagine if we had two such images. They both have the same categories of concepts. They have a woman wearing a dress. They have these two dogs, and they have some birds in the background. And I'm going to think about the model learning the concept for each of them, the concept vector for the dogs, vector for the birds, and so on. And I'm going to get the average vector of each of them. And I want to look at their similarity. Often these vectors are normalized, so I can look at their dot product, and that's an equivalent measure of how similar they are. Now, if all the regions of space that I'm thinking about here, the region that represents the women, the region that represents the birds and the dogs and so on, if they were orthogonal or nearly orthogonal, then that would be great, because when I take the dot product, the cross terms, they basically cancel, they're most epsilon, and I really get a good matching of how similar are the dresses and the woman in the picture, how similar the two dogs, and so on. It wouldn't make sense to be comparing the dog with the birds because these things, they're not comparable in some sense. But of course, these models, they're learning regions of space, but the regions of space that they're learning correspond to actual similarity in our human understanding of the world. So it shouldn't be the case that all these concepts are orthogonal. Like in particular, dog and bird, these are both animals. So one would imagine that they should not be totally orthogonal. And let's imagine that they have some positive dot product because they have some similarity. Let's say 1/4. Now, if they have positive dot product 1/4, then these cross terms do not go away, and they give you this additional term at the end of 1/2. Now, I'm going to do something totally silly. I'm going to now replace the birds in the background with the magic of Gen AI with cats. So now it's a very similar picture, but I have a woman, I have these two dogs, but now I have cats in the background instead of birds. So I haven't changed in some sense how similar these images are. I'm just now I need to compare the cats together instead of birds. But notice that because I've replaced the birds with cats, now I have interference between the cat vectors and the dog vectors. And most folks would say that the cats are even more similar to dogs. So you can sort of see where I'm going here. Now that cats are more similar to dogs than birds were similar to dogs, their inner product should be larger, like 1/3. And so now I have even larger interference. So the point here is I have two sets of images. They aren't really, one pair isn't really any more similar than the other pair, but because of the interference between these non-orthogonal regions of space, I've actually changed the similarity. And so something is off here. So the thing I want to get is if you're just averaging all these different regions, you're going to get these interference between non-orthogonal concepts. And also non-orthogonality is crucial to the idea of representing data in space. So I want to mention one more point, which is a little bit, less in depth, which is that oftentimes, as another drawback of these single vector methods, oftentimes when I'm doing information retrieval, I want to retrieve, say, a document or image which answers my query. And so often documents or images, they may have way more information than the actual content of the query that I have. So if I search, like, show me a painting of a woman and two dogs. Well, this is a valid answer to that query. But just because the painting has other things in it, like a building and birds in the background, doesn't mean that it should not be a valid answer to my query. But if I'm using a measure of similarity, which is symmetric, then I'm unable to measure this kind of thing because I need the property that the query is similar to the answer. But if I switch things around, and a lot of these models, that they're omnimodal, I could just put a picture in and ask for the description. The description would not be characterizing the bird, so the document would not be similar to the query. And so that's only possible if you use an asymmetric measure. So these are two key issues that I want to highlight with the idea of representing data by individual vectors. Yeah.
Use different query and key projection.
Yeah. If you think about them being in the same space and you use different query and key, that's why I said this is a lesser issue. And often with these two tower architectures we have such a thing. But a lot of the times you want to imagine you end up with triangle inequality issues like if this guy the query should be similar to a document and another query should be similar to the same document, but those queries have nothing in common. You basically can look up a factor of two. There's still some issues with this, but you can, depending on what question you're asking, you can solve it with two tower architectures. Yeah.
So there are fine-grained versions of two tower architecture, right? Like the Colbert architecture, for example.
Right. I mean, that's also one of the topics of this talk. Yeah. That's like the next slide.
But you already exist. Okay, so you have another fine-grained.
No, I have nothing new. I'm gonna introduce the Colbert model, and then I'm gonna talk about some of the algorithmic problems that we've studied following up on it. Yeah. So in any event, just to summarize, when we try to summarize all this information in a single vector, we lose a lot. We lose this fine-grained information. And there's, to summarize it in a quote, you can't cram the meaning of an entire bleep sentence in a single bleep vector. And so now I want to sort of like do a thought experiment, a conceptual shift thought experiment, and ask like, what made transformers more powerful than prior language model architectures like LSTMs or RNNs? And these latter two models, that this is not the only difference, obviously, but one thing in particular about them is they had sort of a single state that they kept around, which summarized the entire single vector that summarized the entire state of the sequence that we've seen so far. Transformers, on the other hand, they have a single vector per token in the input, and it's keeping all of them around, and they're all getting to interact with each other. So instead of having a single vector representing the data, it's having multiple vectors. And obviously, many of you already know where I'm going, but we should be designing embedding models that capture the lessons that we've learned from improvements in transformer models, modern LLM architectures. So this, of course, is the natural thing to do is that why don't we train models that in some way output multiple vectors, one vector per data point, and use this multi-vector representation as a more accurate representation of the entire image. So instead of averaging these three vectors, we could output each one of them as a set of vectors. Now, the first question now is, sort of in a algorithm. The first algorithmic question is like, how do we even compare these things? So before I had two vectors, I used Euclidean distance. That's natural. But we need some metric to compare sets of vectors. And so there's a couple natural ones. Folks have studied many different measures between sets of vectors. One of them is the Earth mover distance, or the Wasserstein distance. This is the cost of the minimum perfect bipartite matching between the points. Another one is the closest pair, which is the distance of the closest pair. But, there's issues with both of these that I'll claim. The first thing is that Earth mover distance is expensive, easy, it's hard to train a model with Earth mover distance as your loss function. It's, you need to solve an optimization problem to compute it. And it's also a little bit less robust to outliers because it's requiring a matching, or at least some kind of, flow to be sent through. Closest pair, well, it's useful, but one thing is easy to see, it's actually not more expressive than having a bunch of single vectors and treating them independently. Because if I have set A and set B, I can query each one of these, find the nearest vector in the entire, data set, and that's my nearest thing. So I've gained no more expressive power than I did from just, outputting a bunch of vectors. So instead, and this is coming from this Colbert paper that was mentioned, that the distance measure that's been used, commonly in the past couple of years is this so-called chamfer distance. And I'll mention it because some of you may have seen it called maxim in those papers. I've been calling it chamfer because that precedes that notation precedes by about 20, 30 years. It was used to, this measure used to be studied quite a bit in the geometry, in the image recognition and the literature in like the 90s. But it's a very simple measure. It's I have my sets A and B. I just want to understand for every point in A what this nearest point in B, and then sum up those distances. So, it's, for every point in A, find the nearest B, sum up those distances. It's kind of what you would get if you wrote down the linear program for Earth mover distance, but you killed the matching constraint. So now you're no longer unable to match 2 points to the same vector. You're allowed to do that. And in fact, some points from B can be left unmatched. And then one of the things that happens when you do this is that now you've actually lost symmetry, which is, as we mentioned, one of the things we wanted. So some brief facts about this new measure. First of all, it's not a metric. It's very easy to see that it's not a metric. First of all, because, for example, it's not symmetric. But also, even if you made it symmetric by, say, doing chamfer AB plus chamfer BA, something like that, it makes sense. You still, with a moment of looking at it, it's very far from satisfying the triangle inequality. Like the best you get is triangle inequality up to a factor of the size of the sets. So it's not that, you're really far from being a metric here. Typically, we don't worry about this stuff when we design algorithms until we have to worry about it. But it does capture this idea of containment, which I think is crucial to information retrieval, which is every element of the query set A contained or answered nearby some point of the document set B. So I'm not going to penalize the document for having additional excess information that are not relevant to the query, so long as it has all the information that is relevant to the query. Yeah.
So I guess this actually makes the understanding of the communication invariant. It's like the description, like what is your.
Oh, okay. You mean like the positional, like these vectors for the text? Is there
Description
something?
of the image, and I guess if you like query the coordinate, you go out text, et cetera. The distance doesn't change, right?
Yeah, that's right.
So what is the order actually important?
Like for text,
the order of two images, if I change the order, the word in the description, it actually changes something like that.
Right. I mean, so this distance isn't varying to that. I mean, I guess the one response is that oftentimes you can encode the position when the model is being trained, it may encode the position into these vectors. The other thing is that when we're training these models, when these models are being trained, these embeddings of the different parts of space are contextualized. They're being trained, so they're not independently encoded. So they sort of know their relative ordering in the space, and that's encoded into the embedding itself. So even though the distance it doesn't know about it, presumably the model that trained it does. Okay, so it's sort of obvious to see that this fixes our earlier problem. If we had these three embeddings for each of these three images, each one would find its nearest one. That would almost certainly be the one that's in the same conceptual category in space, and then you get no interference, and you just sum up the distance between each of these. So, and now I want to mention this Colbert paper. So the reason I and others started thinking about this quite a bit is that there's this landmark paper, this Colbert paper that trained such a model, and it was most of this work has been done on text so far, but you can imagine it being done for other modalities. And in essence, they trained a model which generated one token per embedding, and the architecture of this model is very similar to the architecture of many embedding models. Except we just don't pool at the end, and instead of pooling at the end, we overlay a loss function, which is precisely this earlier chamfer loss function, but with a similarity measure. So there's a lot of work on this, and one of the key insights, one of the key results of this paper is that if you do this, you can significantly outperform methods that just use a single vector on many of these common information retrieval benchmarks. For example, these bare benchmarks for information retrieval. Okay, so I want to now spend I wanted to first focus on motivating where this came from, and now I want to talk about sort of the computational challenges that arise when we want to use this at large scale, and also in various applications, especially let's say industry scale. And one of them is that this measure it has a simple form, but it's still much more computationally expensive to compute even the distance itself than it was for a dot product. If I have two vectors, the dot product is computed in linear time. But for chamfer, if I have a lot of vectors, for each one I need to find the nearest neighbor. So this is a quadratic time operation. And so this grows, especially if you imagine using more and more documents, this becomes more and more expensive. More and more larger and larger documents, more vectors per document, this becomes a problem. This is the first thing I want to talk about. The second thing I want to talk about is retrieval for multi-vector models. Like, how do you do nearest neighbor search? I've defined some distance, not a metric, but I can still imagine trying to find the nearest neighbors with respect to this distance. And if I want to use the more expressive power of these multi-vector models for retrieval, then I better have a fast algorithm to do retrieval. And especially in theory, we don't actually have as of yet fast algorithms, sublinear algorithms for nearest neighbor search for this metric. And there's some solutions in practice, and maybe I'll discuss them a little bit later. So these are the two, I think, main computational challenges. There's others, but the two main ones that I want to talk about in this talk. And so I'll begin with the computational complexity of computing it. Let's first talk about, can we get some faster algorithms to compute the chamfer distance? And then we'll see what we can do about faster retrieval. So to begin by thinking about the complexity of computing this chamfer distance, I want to see how does it compare to other, very well understood measures of distance between two vectors. And two of those measures, I mentioned them earlier, but I'll talk about here. One of them is the closest pair, and one of them is the Earth mover distance. So for both of these measures, we actually have, nearly slightly less than quadratic time algorithms. So if you want a 1 plus epsilon approximation, you can do a little bit than n squared time, a little bit better than n squared time. So for example, for closest pair, there was a long sequence of works. Josh has done a lot of work on this. Using techniques from the polynomial method and stuff like that to improve the complexity to n to the 2 minus, let's say, epsilon to the 1/3 is the current best. For closest pair, there's similar things you can do. For Earth mover distance, it actually wasn't known how to get subquadratic algorithms until very recently. A paper of Andoni and Zhang showed how to do this. But still, it's only slightly subquadratic. It's a little bit better than n squared. For chamfer, the exact algorithm is n squared. The best thing we know how to do in slightly subquadratic time is to run an approximate nearest neighbor search algorithm on every point. And that'll return its 1 plus epsilon approximate nearest neighbor, and I do that n times. For one point, it turns out the complexity of doing this is n to the 1 minus epsilon. By the way, this was sort of one of the things that these works were improving on for these pairs, for these problems. But this would be n to the 2 minus epsilon time. But for these problems, we don't have lower bounds, this chamfer distance. So one natural question is this really the best we can do? I mean, is this really in the same category as these other problems? Yeah, please feel free to stop me if there's any questions. So the first thing I want to talk about is result is that actually we can get much faster approximations to the chamfer distance. So there's a paper we had a couple of years ago with Anish Bakshi, Piotr Indyk, Sandeep Silwal, and Eric Weingarten. And we basically showed that you can actually get a near linear time approximation to the chamfer distance. So I give you these two sets, A and B. I can compute a 1 plus epsilon approximation to their chamfer distance in time nd log n over epsilon squared, where nd is a size of the representation. So this is a near linear time approximation algorithm. So this is significantly faster than the almost barely quadratic subquadratic time algorithm that you would get from running nearest neighbors on every point. And so one important point to mention here is if you ran nearest neighbors on every point, not only do you get the cost, but you get the nearest neighbors of every point. So it turns out that actually this is important because we also showed that if you want to return the nearest neighbors of every point, that find the actual map, it's not a matching, but the actual mapping from points to their nearest neighbors, that's even a constant factor approximation. Well, this is essentially impossible in subquadratic time conditioned on relatively well-known fine-grained complexity conjectures. So computing the cost it turns out to be a little bit easier than actually finding the mapping. And so it turns out that this chamfer distance, it's actually much more efficient to compute than these other ones. So not only does it have some of the properties of like being able to represent containment and asymmetry that we want for information retrieval, it's actually also more efficient to compute. Not only that, the algorithm is actually fairly easy and practical. And so I'll go through it here. So we want to compute a 1 plus epsilon approximation to the sum of nearest neighbor distances. One of the nice things about this measure is that it's a sum over distances. The distance is a min, that's kind of difficult to work with, but the sum is not. And so whenever you have such a objective, it's probably amenable to sampling-based algorithms because it's a sum of fixed values. In particular, a very naive thing, I could just sample a random point in my first set A, do a linear scan to find its nearest neighbor in n time, and output that n times that value. And because my point was sampled randomly, that's an unbiased estimator of the chamfer distance, and that would give you, so it's very easy to get an unbiased estimator using uniform sampling. Of course, this isn't going to get us a good approximation because it could be that I have just one point here that's very far away from any point in B, and it's contributing almost all of the chamfer distance. And so if I don't find it, then I'm out of luck. So sampling-based estimators like this are going to have very high variance. So what do we commonly do when the uniform sampling estimator has too high variance? Well, we try to sample from a slightly better distribution. So we can try to use importance sampling to reduce the variance of the sampling. And this is exactly what we do. So if you haven't seen it, the very common technique, essentially what I'm going to first try to do is come up with a rough approximation of all the nearest distances. So for every point A, I'm going to find some value dA, which is roughly the actual minimum distance from it to its nearest neighbor. Let's make sure that it's always at least as large as the minimum distance. How do we bound the approximation? Well, we're just going to ensure that the sum of all those distances is not only an alpha factor larger than the true chamfer distance. So we're going to think of alpha as being the approximation. So if I had an alpha factor approximation to every distance, it would satisfy this. This is actually even a little bit weaker. It says that some points could be a really bad approximation, so long as on average, you have almost alpha factor approximation. Then what I'm going to do is I'm going to sample points with probability proportional to their values. So like if you have a bigger DA, a sample with higher probability. And then for each sample I have, I'm going to actually go through and compute the true nearest neighbor. And then I'll just output this sort of standard importance sampling thing. I output the distances of the points that I sampled, the exact size, but then I renormalize them by the probability that I sampled them, 1 over the probability I sampled them. How many samples do I need? Well, it's proportional to how bad my approximation of the distance metric was. And so really it's going to be, just alpha over epsilon squared, where alpha is my approximation. So if I can get a good approximation, a good rough approximation, let's say a polylog approximation, then I don't need that many samples. And my complexity is n times the number of samples. So the running time would be roughly, really depends on this alpha factor here.
A good question. So what if the sets A and B are asymmetric? Like one is square root n and one is n. What would this, because if you think of retrieval, the documents is B, like B is a document, A is a query.
It's often
the query
bigger.
can be like super small.
That's right, yeah. Everything here still holds. Everything here is more or less independent of n, other than the running time to compute. So note that like the complexity, what are you doing? You're reducing the size of the query and like from the entire query set to a smaller subset of the query. And from those points, you're doing brute force. Query is already quite small. Sampling down isn't going to buy you a huge improvement. So, and sometimes I think of this as being really only significantly useful when your query is complex enough that it has enough vectors and sampling down is meaningful. So, how do we, the key question is how do you find such a rough approximation? Well, it turns out and this seems like something like a chicken egg problem. I'm trying to approximate the thing, but I need an approximation to get an approximation. But it turns out you can get very crude approximations to these, distances in Euclidean space up to polyglot factors in near linear time. And this is the so-called quadtree embeddings. This theory, based on this theory of probabilistic tree embeddings, you overlay a randomly shifted grid, you create a tree based on the randomly shifted grid, and then you find your nearest neighbors using this. And so basically in n log n time, for every point, you can find a log n approximate nearest neighbor. It's a very standard technique. And you just plug this in and you get an algorithm with this approximation. Yeah.
These work like new types of metric spaces or?
Well, they work in L1, and so anything that embeds into L1, for example, like Jacquard's distance and L2, LP distances would be larger than 1. It'll work for them by that embedding. Depends on what metric you had in mind. I mean, yeah. Most metrics that are more complex than L1, you try to embed them to L1. Yeah. Well, there actually is a technique for general metrics based on these Bartol trees and FRT. So that if I one point, these things are very efficient. If you don't need efficiency, if you just want to create some hierarchical tree with this approximation, there's in any metric space, endpoint metric space, you can create such a tree with this log n approximation. But it's an offline algorithm. It takes maybe quadratic time to compute this thing. These are called Bartol trees or FRT trees. And so these sort of algorithms are mostly useful when I'm thinking about very larger scale sets of points. Obviously, as you mentioned, if my query only has 8 vectors, this is not the algorithm you're using. But we ran this on a bunch of different data sets, even at the 100 scale, and even at the 100 scale, you get improvements. At the 1,000 scale, you get significantly more improvements. I think everything here is on the 1,000 or higher scale. And so the algorithms were, roughly, even at this small scale, the number of samples you need is maybe like 5 to 10 times smaller than if you were uniformly sampling. That's the natural thing that you would do otherwise, is uniformly sample. And not only is it more sample efficient than uniformly sampling, one advantage of uniform sampling is you don't have to create this coarse approximation. Turns out the coarse approximation is very fast to compute. It's a very simple algorithm. And so you still get a pretty good speed up even if you don't do this.
That log n, if you have these two sets of size n1 and n2, that log n is, what n is that?
Well, I think it's the second end. What's happening is you're looking at contraction of the plot tree, and it's a union amount over all the points that it's basically it's the number of pairs. It's a number of pairs, yeah. Because it's bipartite, no, it is just the number of points in D. Yeah, it's log of it. It's the second side. Because you can just think about like each point, you only match it to points in B, and so how many distances do you use a union bound over shrinking? Okay, so the point of we scaled it up to billion scale data sets. You probably wouldn't necessarily run this on a billion scale. Well, one of the a side application of this sort of look at similarity between data sets. You can imagine you have 2 billion scale data sets. Maybe I don't want to do retrieval, but I want to understand how similar they are. And this is one method to do that. And we actually we pulled the big ANN data sets and like the whole data sets and use them to like different subsets of them in the entire data sets and look at similarity. And it turns out that it's very easy to scale to these things. And you do get obviously 50 times faster than brute force methods like KD trees. But I want to move on from here. The key takeaways I want to get at are that this chamfer distance captures it has more expressivity than just using a single vector. And other methods of comparing sets of vectors, while they're natural, and the chamfer need not be the golden ticket. It's not clear that this is the only way to do this kind of thing. And in fact, it probably isn't. But there's computational advantages for using this chamfer distance because it can actually be approximated very quickly. Not only that, it's easy to train with it, and it also has sort of this nice expressive capacity that it sort of models a metric version of containment. How much is that contained in the other set? It's also more amenable to sampling-based algorithms because it's a sum. So in the second part of the talk, I want to discuss this other, perhaps arguably more important problem of information retrieval under this measure. The original, works that introduced these multi-vector models, they were focused on this task of retrieval. And to get good retrieval, you need a good model that represents your data, but you also need a good algorithm that does the retrieval. And because we now are changing the game a little bit, and we're no longer doing single vector retrieval, we need a new algorithm for this. And so I'll just, this isn't a metric, so it doesn't conform to this, nearest neighbor search definition that I said earlier, but the problem setup is exactly the same. It's just that it's no longer a metric. I have some data set of points. Each of these data set points, each point in the data set is itself a set of points inside of the metric space, RD. And I'm given my query, which is again a set of points vectors in a metric space, and I want to find from the data set the nearest neighbor in terms of this chamfer distance. So it's very well defined, even though, and I could ask for a C approximation as well. And I'd like sublinear end time. So this is the same goal. So the first thing to mention is that we have bad news, and that's that this goal is essentially unachievable. In essence, what you can show is that for any arbitrarily small constant epsilon, if you have any algorithm that solves this problem in time, even if you allow polynomial and n pre-processing time, it can't solve this problem in less than in n to the 1 minus epsilon time, unless SAP is false. It's a orthogonal vectors conjecture lower bound. So essentially, you're not able to get a subquadratic sublinear time algorithm for this problem. And why is that? It's actually, for anyone that's seen these kinds of reductions, it's fairly easy to see. One problem that's actually hard to solve in sublinear time is I have a bunch of sets A, a bunch of sets of B. I want to ask, is one set A contained in the other set B? And one interesting thing about chamfer is that if you think of it as if you're working with sets, if A is actually contained in B, then chamfer AB is 0. If you're on multiplicative approximation, you better be able to distinguish between your query being contained in the data set point and not being contained. Any multiplicative approximation must do this. So sort of any multiplicative approximation is going to be able to solve this subset query problem, and therefore n applications of it will solve the orthogonal vectors problem. So this is sort of why why we can't solve this. And then you look at this and you say, okay, well, what's the issue here? The issue is that if A is contained in B, that a multiplicative approximation needs to find it because it's a multiplicative approximation. So can we try to avoid this and come up with an additive error algorithm? And can we get sublinear algorithms with that? So what would additive error look like? Well, we first need to understand some notion of scale for additive error. So let's go ahead and normalize all the vectors in my set. We'll put them in the unit sphere d dimensions. If I do that, then note that the chamfer distance is a sum of number of things in the query set Q. So it's always between negative Q and positive Q. Well, it's actually each one of these guys is between -1 and 1. So each one is the most 2. So the sum of the most 2 times the size of the query. There we go. Okay, so we have some sense of scale. So what would our additive error be? It would be roughly epsilon times the size of the query set. Now, the first thing to note is that the lower bound on the prior thing, it only needed these query sets to have size like at most log n. So the second that epsilon is less than log n, you're somewhat solving the multiplicative problem here. So we can't hope for algorithms that are polynomial in epsilon, and this is still an open problem, and this is the first open problem I want to mention. One could naturally hope for algorithms that are exponential in 1/epsilon, or even let's say n to the 1 minus epsilon, for this additive error chamfer nearest neighbor search. And in fact, I expect algorithms of this form to exist. The reason I think that they need to be n to the 1 minus epsilon is because you're at the very least are solving 1 plus epsilon approximate nearest neighbor search in the regime that the points have sort of a constant size. And even if all the sets have size 1. So I expect that this is sort of the right answer, but for the moment I don't have an algorithm for it. Okay. This started at noon, right? Or about 5 minutes, noon and sometimes okay. Great. So the last sort of approach on this that I want to talk about is the if we have this metric, we don't have necessarily provable algorithms for it yet. But a common thing we do in TCS is when we have a complex metric, we don't understand it very well. We try to embed it into a simpler metric and use algorithms in that simpler metric that we have already, and also use our understanding of that simpler metric to understand a more complex one better. And what is the natural one to embed into? Well, in practice, people use single vector nearest neighbor, and in practice we often use similarities. Dot products are easier to compute on hardware. So we're reduced to this problem of reducing chamfer nearest neighbor, most similar neighbor to maximum inner product source, just so-called MIPS. And so here I have my data set and I want to find the one that has the maximum inner product. It's the same thing as minimizing Euclidean norm if they're all unit vectors. So why is embedding into inner product, why is this the right metric? Well, very, very fast maximum inner product search algorithms exist in practice. Turns out maximum inner product search is also, you can't necessarily, well, it's a similarity, so multiplicative approximations don't make so much sense, but for very similar reasons, there's lower bounds for good enough additive approximations for maximum inner product search. So in some sense, it's not easier in theory, but it is, in practice, we do this all the time. So can we embed, our complex measure, this chamfer distance, into a single vector dot product? And I think this is sort of a fundamental question, because we understand from a lower bounds perspective, if you cannot, then that shows that this is a much more complex metric than single vector. From a lower bounds perspective, if we can, then we can get faster algorithms by embedding our sets of vectors into a single vector and then using algorithms for single vector. And so the first result I want to talk about along this line is this paper we had last year with some folks at Google. And what we showed is that you can in fact do this. You can design randomized embeddings. There's a different embedding for the query and different for the function for the document. That's necessary because I want to embed it into something that's symmetric, which is an inner product. So my mapping better be asymmetric. And so these mappings, they embed sets of vectors into a single vector such that the single vector dot product is an epsilon additive approximation of the chamfer similarity. With probably, these are randomized functions, so probably 2/3. And if you wanted a failure probability here, this is like log 1/2 epsilon to kind of see the dimension. But of course, what is the dimension? That's the key thing going on here. The dimension, if S is the maximum bound of the size of the sets, the dimension is S to the 1/epsilon. And the next question, this is sort of you can also use it as a JL style result. I can actually concatenate this embedding log 1/delta times or log n times, and then I can embed n sets of points. And so you can indeed use this for nearest neighbor search, which is what we do in that paper. It's actually more of an experimental paper. So you can think of this as like a JL style result, but we still don't know what the best dimension here is. And this is so the next problem I want to mention is what actually is the lowest dimension that you need to embed multiple vectors into a single vector. You can sort of show a lower bound that you can't do better than the dimension times the number of vectors to begin with, which actually is not trivial because if you think about it, JL says you can reduce a single vector to something less than the dimension independent. But here you can't actually reduce to less than S, the number of vectors. But that's the best lower bound we have, S times D. If we can prove a better lower bound, that would strongly separate, these two things. Because remember here, in the multi-vector world, we have S times D coordinates. And in the single vector world, if we cannot have, if we need more than S times D, then there's separation. But this is still open at the moment. I should mention one more thing. We now have there's also deterministic algorithms for this. So we've recently made this whole thing deterministic. You can actually do it based on the polynomial method. And so it would be interesting even if we could prove lower bound on deterministic embeddings. Like, can you not embed the entire space with error epsilon? That we don't even know how to do. So I'm gonna skip over the construction here for time. It's fairly happy to talk about it offline. I just want to mention one last thing, and that's that, as we mentioned, this whole chamfer thing, it's not clear that this is the right function to understand. It has some nice properties, but there's some downsides as well. In particular, we don't get good fast approximate algorithms for nearest neighbor search. On the other hand, this more complex metric, Earth mover distance, we actually do get sublinear time very fast algorithms with small polylogarithmic approximations for nearest neighbor search. So you can actually get an algorithm for Earth mover distance, retrieve the approximate nearest neighbors with an approximation of log S/epsilon, nearly linear time preprocessing, and so on. And so this is what you would want, but of course EMD has other trade-offs. So another I think impactful direction, both on the theory side and on the practical side here, is to see whether there are actually better similarity functions used here that still have the expressivity. They still relax earth mover distance, as chamfer does, but they also admit sublinear time multiplicative approximations for the distance nearest neighbor search. Such a function, would be useful both in theory and practice. So I just want to end there, and thanks everyone so much.
So, in the follow-up book from Colbert, there seems to be this consensus that Colbert's really good for ranking a small set of documents once you retrieve them, but not really much better than, standard retrieval, at least in the text domain. And that's because they have a suboptimal, like in light of your talk, they have a suboptimal retrieval, right? And you have a better retrieval. So have you tried like using an off-the-shelf BOT model, Colbert model, and seeing if, your retriever improves the retrieval performance?
So comparing what to what? Comparing multi-vector on the same backbone to single vector on that backbone, or?
Yeah, so, comparing Mubera to the retrieval method recommended in the Colbert paper, which is something different and suboptimal.
Right, yeah, so it beats that quite significantly in terms of latency, or like comparing latency versus
No, what about precision recall?
That's what I meant, the latency recall
Oh, okay.
curve, like the ratio curve, it beats that. And it beats, so there's a follower to that called Plaid, which was, significantly more efficient. And we beat that on, I think, 8 out of 9 data sets from the Bear thing. And the one we didn't, we sort of matched it on one of them. So I think there are even more improvements of that. Although, we still have, there's a ton of engineering work to do on this that I think can speed it up further. So I think there's some headroom there. But it's not clear that there's a lot of different ways you could try to approach this retrieval problem. And this was a fundamentally different one than that one. So I think there's still a lot of new engineering work to do on this new system that had already been done on the last one.
So if you got like a picture with 100 dogs and 1 cat, and a picture with 100 cats and 1 dog, I guess that's another situation where the chamfer distance is small, but the person for distance is big.
Yeah, I mean, I guess one would hope that you capture all the dogs into one vector instead of having a different vector. So here, actually, even if you don't, I think one thing that I sort of glossed over is that these embeddings, they know about each other. So when I embed the 100 dogs, every embedding of a dog knows that there's 100 other dogs.
Oh, I see.
And so, now we can get a little bit speculative, but like you can imagine that the fact that it's a dog amongst a group of dogs is in the region of dog embedding space, there's vectors further away that correspond to groups, a dog amongst a group of dogs. So, I mean, in text is a similar thing. You sort of know about your context a little bit. So that would get you around that. But I agree that if you didn't do that, then earth mover distance would capture something that this does not.
Let's thank Raj again.